So last session we discussed on global system for mobile communication. ITU have given its recommendations for usage in the specific countries, specific bands, very specifically spectrum bands could be vary from country to country. So it had emerged, or this would be the generation and it started with the SIM card. First generation mobiles don't have SIM card. It's a handheld system fixed with the ASIC, application specific integrated circuit. First generation mobiles are ASIC actually. From second generation onwards, that we are getting data, voice separately. Third generation, voice plus data. Fourth generation onwards, people started working with the data rate. Right? So, what would be the role of GSM? So, still we are learning a lot about GSM with repeated data. Okay, so that would be the best one. Yes. Now, let us refresh the GSM architecture again. We will understand it in some other pattern. The building blocks of GSM architecture need to be remembered always, right? So that's the case. So I think this animation will help you to understand it in a refreshing way.
A mobile telephone call is a simple process. In reality, this call is only possible thanks to a complex network architecture consisting of various different network elements. In this lesson, you'll get to know the individual elements of the GSM network and their basic functions. The base station subsystem, BSS, provides the connection between the mobile stations and the network subsystem, NSS. The NSS forwards user signals to other mobiles via the BSS, or subscribers in the public switch telephone network, PSTN, and provide necessary customer data. The Operation and Maintenance Subsystem, OMS, monitors BSS and NSS performance and remotely debugs occurring faults in the network elements. Additional components such as interface elements to data networks, the short message service center, or the voicemail system complete the GSM system architecture. The base station subsystem ensures as complete network coverage as possible and includes a large number of structurally organized radio cells. It consists of the following elements: the base transceiver station, the base station controller, and the transcoder. The central element of one cell of this kind is a transmitting and receiving unit known as a base transceiver station, BTS. This makes the connection to the mobile station via the air interface and controls the transceiver, TRX. The transceiver, the central functional unit of the BTS, maintains calls to a maximum of 8 mobile stations via one frequency pair each. The BTS is also responsible for the monitoring of the signal quality and the encoding and modulation of useful signals. Via the ABIS interface, it forwards calls, signals, and control information destined for the OMS and the NSS to the base station controller, BSC. Several BTSs are controlled by the base station controller, BS. This assigns 3 radio channels in the TRX to the link to the mobile station. It controls necessary output power for mobile station and TRX. It monitors the existing radio link to and from the mobile station and controls the handover between neighboring radio cells if they're under its control. During an existing radio connection, the BSC monitors its quality and controls disconnection of the radio link when the call is over. The BSC communicates with the transcoder, TC, via the editor interface. The transcoder is the third element in the BSS and is needed to convert 64 kilobit per second original speech into a 16 kilobits per second signal of speech description parameters to ensure a spectrum-efficient modulation on the air interface. BTS, BSC and TC together form the base station subsystem, BSS. The base station subsystem forwards signals to the network subsystem, BSS, where speech and circuit switch data are controlled and forwarded to other networks if necessary. The NSS provides data relevant to security and mobility. The speech signals processed by the transcoder reach the Mobile Services Switching Center, MSC, via the A interface. The MSC serves as a digital exchange for forwarding of messages, connecting mobile subscribers with each other or with subscribers in other networks, such as the public switch telephone network, the ISDN network, or data networks. The MSC is responsible for the following functions. It forwards incoming and outgoing calls. It makes a connection to other MSCs in the same mobile radio network and makes connections with other mobile radio networks and to fixed networks. It monitors and controls the calls. It is responsible for call data acquisition and the forwarding of signaling information to connected registers or databases. In order to monitor, route and control mobile telephone calls in GSM networks, several registers are connected to MSC. One of these registers is the Visitor Location Register, VLR, which is usually to be found in the MSC, but is a functional unit in its own right. It is designed as a dynamic subscriber file with dedicated geographical areas of responsibility, the so-called location areas. The VLR acquires the data of all GSM customers in its areas and is always well informed of their whereabouts. It assists the MSC in the acquisition of charge-relevant data with subscriber information. The bills are prepared from these data in the billing center. But where does the VLR get the GSM customer?
So this is an important point. Even most of the campus interviews, people have raised this question. Even people are going from circuit branches. Not only for ECE, even for CSE and IT students, they have raised this question. How about the billing of your communication strength has to be measured? That should be done through MSC only, right? Using the DB of VLR.
Customer data from. For GSM customer data acquisition, there is a register, the so-called Home Location Register, HLR, in which each network operator registers the customer data necessary for dealing with traffic. The HLR supplies these data to all VLRs in which the GSM customers involved are to be found at any given moment. Inversely, the VLR in question informs the HLR of the location area of the customer, and is thus able to give routing information when calls come in. The HLR data contain information on access rights with regard to roaming, service rights with regard to voice, fax, and data services, and additional subscriber services. The Authentication Center, AUC, contains the customer data necessary to protect connections against unauthorized access, and is mostly integral to the HLR. The AUC checks the information stored in the subscriber identity module, that is the SIM card, for correspondence with its own register. If the data proves to be identical, the authentication of the subscriber is successful and is given permission to enter the network. If the SIM card is stolen, authorization to access the network is disabled very easily by the AUC. Additionally, the AUC provides necessary information to cipher the end interface. The Equipment Identity Register, EIR, can be implemented as an option by the network operator. The EIR permits the detection of stolen terminal equipment used in GSM networks by checking the IMEI, International Mobile Equipment Identity, against the data stored in the EIR. This check is carried out independently of the SIM card and only applies to the mobile station in question. All the components which control and forward the call and are responsible for security and mobility management, that is, the MSC.
So these could be the main functionalities of MSC: call forwarding, control, security, and mobility management.
HLR, VLR, AUC, and EIR.
These are all the components of MSC: HLR, VLR, EIR, and AUC. Authentication Center, Equipment Identity Register, Visitors Location Register, Home Location Register. These are all the components of MSC. Functionalities of MSC are call forwarding, control, security, and mobility management, right? You could expect these things in 2 marks, part A.
For the Network Subsystem, NSS. The GSM network is monitored and controlled from a central point. This is the Operation and Maintenance Center, ONC. The ONC has the following tasks. The Fault Management System analyzes alarms from the BSS elements. When faults occur, they are eliminated when necessary via software command or in situ by technicians.
This would be normally maintained by the service provider itself. If the towers are being erected by the respective state government, means that will be taken care by the telecom authority of respective state government. If it is going to be overall India, I think from next year onwards, TRAI is taking this control over on the, I think in the budget they have announced. TRAI have taken its complete control. Here onwards, any tower erection that is going to happen for mobility, ultimately that should be with the approval of TRAI only. So they have taken their complete control. So these operations, this OMC will be taken care by the TRAI itself.
The Configuration Management function installs the software when new BSS network elements are implemented, manages hardware inventory lists, and changes operation parameters, for example, for radio frequencies of a BTS. The Software Management System feeds in new software, or updates and manages the software inventory lists. The Network Management Center, NMC, assumes special functions in the context of ONS, which are not defined in the GSM standard, but are based on definitions of the International Telecommunication Organization, ISO, and on recommendations of the International Telecommunication ISO. An NMC carries out functions of performance management. Alarms and elimination times are evaluated statistically. Capacity bottlenecks in the network are detected, and the service quality is monitored, for example, the drop call rate in %. Depending on the network operator, the NFC functions are carried out in a centralized or decentralized way in the geographical areas. All NMC and OMC of a certain defined geographical area form the third subsystem, the Operation and Maintenance Subsystem, or OMS. The three subsystems, BSS, NSS, and OMS, are vital to the operation of a GSM network. The interfaces within and between the subsystems are mostly specified by the ETSI. For dealing with customer support and supplying service services, GSM includes a number of additional components. The Administration and Billing Center, ABC, transfers customer data to the appropriate registers of the NSS into the AUC and the HLR. The Administration Center is connected to the Personalization Center for SIM cards, PCS, via an interface. This makes it possible to disable the SIM card if necessary and protect it from abuse. The so-called call detail records are used in the Billing Center for bill preparation. The Voiceline System, VMS, is a memory system for voice, data, and fax messages spread over the net. In other words,
they recently introduced this application here. That is the point where they started integrating, where they have started integrating their voice plus data, irrespective of the speed.
a large-scale answering. If a subscriber has switched off his mobile station,
Class
for
one, class like
other reasons, the messages are not sent to his mobile station, but are fed directly into the VMS and stored there. The subscriber can either request them from the VMS or he's notified via SMS. The VMS can have interfaces to several MSCs and to the Short Message Service Center. Via the Short Message Service Center, SMSC, network operators, service providers, and private customers can send short messages directly onto the mobile station of any subscriber. In the SMSC, the short messages are stored temporarily and forwarded to the recipient. Point-to-point short messages are alphanumerical messages with a maximum basic length of 160 characters, which are entered directly via the keyboard of the mobile phone. Compression.
Now we are getting the feature that if you are going to type more than the specific number of characters in the SMS, by default it will split the SMS into multiple number of SMS, or it will be converted into MMS. That could be done through the protocols which are available in the application layer.
And concatenating techniques increase the number of transmitted characters. The cell broadcast SMS, that is, the service offering point-to-multipoint short messages, is a one-way communication from the network to all mobile phones in certain geographical areas. The messages, with a basic length of 93 alphanumerical characters, are entered in the OMC, fed centrally into the BSC, and transmitted to the mobile stations via all connected BTSs at regular intervals. In order that data can be fed into a GSM network from packet switch networks, such as the Internet or company intranets, a so-called interworking function, IWF, is required. This is an external data server connected to the different data networks. The IWF translates the unstructured incoming packet switch data into circuit switch signals, which can be understood by GSM. A firewall upstream of the IWF protects the GSM network from unauthorized access by hackers. In GSM Phase 2, only circuit switch data services are supported. The interworking function, IWF, integral to the MSC, connects the circuit switch GSM data traffic.
IWF is a router. Be frank, if you want to say in the terms of computer networks, it would be a router.
To the existing packet-oriented networks, in other words, the Internet, corporate networks, public data networks, and web servers. It converts protocols and adapts the data rate for the BSS. In GSM, the public land mobile network, PLN, is a cellular network with a hierarchical structure. The smallest unit is the radio cell, which the BTS supplies with frequencies, or, in other words, radio channels. It provides the network coverage. Several radio cells are put together to form administrative areas controlled by a BSC. Various areas controlled by one BSC each form a location area controlled by a VLR. It is also possible for a location area to cover one BSC only, or even one cell. If a mobile phone subscriber changes to a new location area, a location update takes place automatically. So the location of the subscriber is known to the network via a VLR linked to the MSC. If the BTS is in the center of exactly one cell, you speak of an omnidirectional radius. The BTS transmits its frequency with omnidirectional characteristics and a high output. Omnidirectional radio cells are used particularly in relatively sparsely populated rural areas. In densely populated areas, though, the network must supply higher capacities. One way of doing this is the sectorization of radio cells. With a sector radio cell, the BTS can supply up to 3 radio cells and 3 times 120 degrees, with several frequencies each. On motorways, base transceiver stations are preferentially configured in 2 sectors. For example, the BTS transmits frequencies in 2 times 180 degrees. The cell is aligned along the course of the road to be covered. In densely populated cities, we often find a combination of omnidirectional cells and sector cells. This is because there can often be zones of missing coverage between sector cells. A superordinated omnidirectional umbrella cell is the
Pertaining to GSM, the antenna design also have given a wide fluctuation in the environment. That is the reason why antenna design has been restricted and standardized as per the norms of TRI. ITU have given recommendation such a way that every service provider should not design their own strong beam antenna or moderate beam antenna or low beam antenna. It won't be like that. The thing has to reach every customer in the same fashion, right? So to avoid that, TRI have regulated in India that construction of the antenna would be based upon the recommendation given by ITU and to be verified or vetted by TRI, Government of India.
over the radio supply to scattered individual mobile stations located in these locally occurring reception zones, and for rapidly moving mobile stations used on motorways and in high-speed trains. Rapidly moving mobile stations in particular are supplied via the larger umbrella zones in order to avoid as far as possible handovers taking place in rapid succession. In order to supply
So this could be the old style what they are conveying now. That, but nowadays it won't be like that. We will get service access point whenever we are in mobility. That's the case. Right? If I'm traveling in train, I could be able to access the internet through my service access point available in the train itself. The process of roaming will be eliminated here. Accessibility within that restricted environment could be managed through the location register easily.
areas with a large number of mobile phone users, so-called microcells are used. Thus, for example, BTS with a low output are used in underground stations. These take over the radio supply on the platform or with special antennae in the subway tunnels.
So that's the discussion about the refreshment of architecture. The subsequent one is nothing but how this connection establishment or the protocol is happening between the sender and receiver in GSM. So we continue from the morning one.
By the BSS, the appropriate serving MSC. A location update request to be controlled in VLR. This then requests a subscriber ID for receipt of a mobile station, which is sent immediately to the VLR. Now, the VLR can request the authentication data, also called the authentication triplet, from the subscriber's HLR AUC. After receiving a reply from the HLR, the VLR sends authentication data to the mobile station. After successful authentication, the location update, including the VLR address, can be sent to the HLR subscriber as the current location. Let's have a closer look at the authentication process. A new serving VLR requests authentication from the SIM card user. This request is forwarded to the Authentication Center AUC of the home network.
These are all the protocols involved in the respective phases.
Provide the VLR with an authentication triplet. The triplet consists of a random number, RAM, a signed response, SRES, and a key, KC. This
Triplet represents a three variables.
XRES is the calculation result of the algorithm ARE, combining the individual key KI stored in the AUC and the random number command. KC is generated in the same way by the algorithm A8 using rank. Several of these triplets produced this way are transmitted to the inquiry VLR. The VLR first stores both prototype triplet, KC SRES, for later use, and only transmits the random number rank to the mobile station. Using this number and the information stored on the SIM card, that is, the algorithms A3 and A8 and the key KI, the mobile station can produce the same parameters as the AUC, namely SRES and KC. For authentication, the mobile station sends the SRES it's produced back to the VLR. The key KC is used later to channel. Now, the VLR.
So it is running like an asymmetric cryptography, right?
Can compare both SRES numbers, one from the mobile station and one produced by the AUC. If both parameters tally, authentication was successful. Finally, the TLC is transmitted in encoded form. We refer to a mobile terminal, MTC, when a mobile subscriber is being informed. Let's look at the MTC using a call from PSTN as an example. First, the PSTN customer dials the number of a mobile phone. The number dialed is the MSISD number. The exchange of the public switch telephone network, PSTN, analyzes this number and contacts the Gateway Mobile Services Switching Center, GMSC, that is, the link between the PSTN and the mobile network. The GMSC doesn't know the current location of the call subscriber, and therefore starts a remote inquiry to the HLR of the call subscriber. The HLR checks its database entries to find the current location or the currently serving MSC VLR of the call subscriber. Now, the HLR asks the serving MSC VLR for the route information necessary for the call connection. The serving VLR now generates the temporary mobile subscriber roaming number to SRM and sends it via the HLR to GMSC. The GMSC now has the written information it needs and transmits the call onwards to the serving MSC. The VLR makes the LAI available to the call subscriber. To locate the call subscriber, the MSC initiates the paging process within the location area. Let's have a closer look at this process. The MSC initiates the paging in the entire location area using the temporary mobile subscriber identity, TZ. This is made available by the VLR, and it's also known on called mobile station. It's been allocated to a subscriber after the first location update of his mobile station, and is used instead of the users for data security reasons. Within the relevant location area, the TZ of the called mobile station is broadcast on the interface via the paging channel PCH. However, as the TZ is being allocated within the VLR area, and thus also the location area, only the called mobile station identifies the paging channel and reacts accordingly. The called mobile station reacts to the paging channel with a request to the network for a free channel. This request is sent by the random access channel RACH in an uplink to the VXS. This outlays through the access grant channel ADCH a standalone dedicated control channel SDCH to the mobile station. This communicates with the VSS via the SDCH, which exists both in the uplink and the downlink, until a traffic channel is allocated to the mobile station. Parameters for authentication and encoding, as well as the new TIMs, are transmitted via the SDCH to the mobile station. If this is concluded successfully, the actual call setup is initiated. For this purpose, a voice VSS by allocating the traffic channel on the air interface. Let's have a more detailed look at the various steps of call setup. First, the mobile station is informed that incoming call requires a call setup. This setup message is sent to the mobile station via an SDCC. The mobile station confirms the setup inquiry incoming via the same channel. Now, the MSC selects a terrestrial channel that contains units, also called a trunk, for transmission to the VSS. It sends a message and assignment request message to the VSS, asking to allocate a free resource on the air interface. This message contains information on the trunk views, so later on the data stream functions further. After receiving the assignment request message, the VSS allocates a suitable traffic channel and transmits this allocation via the SDCCH to the mobile station. This must now prepare itself for a configuration of its edge. The mobile now takes over the allocated traffic channel and transmits the confirmation of the allocation to the VSS via the FACCH. Now, the subscriber is informed for the first time by the man-machine interface (MMI) of the incoming call. In other words, the telephone rings. The VSS transmits a final confirmation message to the MSC about the successful allocation of the air and terrestrial resources. If the channel allocation is unsuccessful, the VSS sends an appropriate error message to the MSC about the reason for the failure. Possible reasons for a failure are that either air or terrestrial resources were reserved previously and are thus unavailable. Speech and signaling data are not transmitted in their original state of the interface, but are encoded. Only after successful authentication can the BTS in the mobile station start the encoding process. The 114-bit key used for encoding and decoding at both ends of the air transmission is produced at the BTS and at the mobile station using the encoding algorithm A5. For this purpose, A5 uses the 64-bit key KC that was generated during the authentication process, and the 22-bit TEMA frame number in order to encode and decode speech and signaling data. We refer to a mobile regulated call as MOC, when a mobile telephone subscriber is subscribed to the public switch telephone network, or on a public area mobile network, VNS. The mobile caller dials a number. This means he starts a call service inquiry in the network company visitor. Then, the net analyzes the call subscriber data to do three things: to authorize or refuse use of the network, to activate the requested service, and to route the call. If the call is addressed to the same mobile network, the MSC turns the relevant HLR by the government ISDN to send the call to its destination. If the call is to the PSTN or to a different PLMN, it's routed there by the gateway MSC to the MSC and sent on to the target subscriber. If the call is made to a PSTN, the following communication procedures take place between the network vendors. First, the VSS and the mobile station agree on channel allocation. When this is done, necessary safety checks related to the subscriber are carried out between the mobile station and the serving MSC alarm. The mobile check is optional, depending on the network operator. The email, which is transmitted in encoded form through the air by the mobile station, is sent to the equipment and series and checks the authorization of the terminal used. Only after the security checks have been carried out and the mobile station start the call setup via the MSC. This now checks, in the case of VLR, whether the subscriber is authorized for the desired service. If the VLR says that call is required, the call setup can be carried out, and a traffic channel can be allocated to the connection. The serving MSC sends the call via the relevant GMSC to the exchange of the PSTN. If a confirmation of successful call setup is sent from there, the caller is informed by his MSC, and he hears the calling signal on his telephone. The conversation can start. We know already that the GSM network is of a cellular design. If a subscriber moves from one cell to a neighboring cell, the current connection must be maintained without any interruption. To ensure this, there is the handover. That is, the neighboring cell takes over the current tasks in a sort of substitution without stopping, and the connection to the original cell is interrupted. Handovers occur in the following cases. A handover due to transmission measuring results occurs when the signal strength or its quality is too low, or the distance from the mobile station to the BTS is too great. The call is then transferred to a neighboring cell. A handover due to high traffic volume within the cell occurs when the capacity of the cell is exhausted, and the call is transferred to a neighboring cell which is less busy. When necessary, a handover can be paused by the OMC due to maintenance work in the cell. A distinction is made between various handover types. We'll look at them in more detail in the following lessons. The smallest of the handover types is the handover within a cell, the intra-cell, intra-BSC handover. In this case, the subscriber is diverted to a different traffic channel within the same cell. Generally, this channel is generated with the previous time slot. The decision about the handover is made by the BSC that controls the cell. The inter-cell, intra-BSC handover takes place when mobile user moves from one cell into a neighboring cell, both control the same BSC. The traffic connection to the old cell is continued as soon as the connection to the new cell is successfully completed. This process is controlled by the BSC. We refer to an inter-cell, inter-BSC handover when a mobile user moves from one cell to a neighboring cell is controlled by a different BSC. In both BSCs, it is required by the same MSC. This type of handover is carried out by the operating MSC, but the decision about the handover is made by the old BSC. The connection to the old BSC is only interrupted when the new connection has been successfully established.
So, especially the handover procedure has been illustrated in very detail. I think this had given a wonderful information that the three situations where handover procedures are being projected to be measured. Don't forget about that. Components of GSM architecture to be remembered. That's what still the last four sessions that we are focusing on this GSM components, right? So that's the case. All are informed to post your complete roll number in the chat.